तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were analyzing waveforms of a counter in the last class, and we will continue to do the same in this. And as you see, a counter has a reset input, and there is further a reset counter here, which will take place only when counter reg, which is running counter, is equal to 255. So this setting point can be changed if you wish, another setting here, and you can advance the counter when this condition is satisfied, that is ABC being 1 each, and of course there is a clock which is reckoned at a positive edge, and finally there is an 8-bit counter whose output is displayed here. And we have also seen the actual design wherein this reset count is when counter reg is equal to 285, and we advance only if A equal to 1 and B equal to 1 and so on, that is ABC being collectively equal to 1, and we increment the counter register, this is a pre-incrementation, and so we which will take effect only during positive edge of the clock, and that is at this point, and these are all nothing but clearing the counter when reset is encountered. And this is also corresponding to register being counter being 255, and then also you need to make the counter 0, clear the counter, and you count only when advance count is active here, and this was pre-incremented earlier, and we merely assign here in order to speed up the operation. And so if nothing else is satisfied, in fact all aspects are covered here, and so you need only to it is a dummy statement wherein you do nothing, just preserve its contents. If you dispense with this, then also it will work. So that is the end of this counter, and let us have a look at the waveform that we had it earlier. So here the counter next is depicted here. I will improve the zoom after a while, and you can see that it is pre-incremented, whereas the counter reg itself is only I am sorry, this is not the right thing. So this is the one. So you have a reset signal. When reset occurs, irrespective of the clock edge, you clear the counter as such. This counter reg is here, it is cleared to 0, and you notice that counter next is incremented by 1 right here. So this is what I meant by pre-incrementing, and so ABC are in binary progression being the inputs as such, and when ABC are 1 each, that is at this point, then only the advance count goes high, and hereafter once it goes high, then only the counting starts. Until then it was all 0 here right up to this point, and the actually counter reg goes up by 1 only with the arrival of the next clock pulse here. That is after advance count is activated, and this is a combination circuit as such, being a realization of ABC here, and we will just zoom it so that you can have a clear view of this. So, you can see reset clock ABC are the inputs, and first one is reset count here. You can just have a look here, and with the reset this counter reg is cleared right at that point of time. This is the last one is counter reg, and you can see the time axis clearly here, 50 nanosecond and so on. So, it is around I think 20 nanosecond it goes to 0, and that is what we had put in the test bench, and here it starts incrementing only at this edge. So, you can see that this is the edge that is at 150 nanosecond, and corresponding to that clock has become active there. That is a rising edge of the clock is noticed, and here ABC conditions are 1 here, 1 here, 1. This is ABC, and reset is no longer active. It is active during low phase here, and you can see the counting progressing smoothly by 1 at every clock pulse. If you have a look, it will be a clock pulse here. So, rising edge of the clock pulse here, and once again it will rise here. So, again you can see at all points of time this counter next is pre-incremented here, and going to the next waveform, which is a continuation of this, we will have. So, once again you can rest assured that all the other points were clearly counting, and what is shown here is a snapshot of the end point. So, when it is approaching 255, what happens, that is what matters, and being offline the waveform view. So, I think it would be better to have start and end point, that should make it very clear to you. And you can see here it is counter reg is 250, 251 and so on, corresponding to 250 it is a pre-increment. So, it is 251, and right at this point of time here you notice after 255 it is counter next has become 0, and this counter 255 is appearing only at the next clock edge here. When it is 255, this reset counter, which is a combination circuit of sensing counter reg equal to 255, which happens right here, and immediately it goes high, being a combination circuit, and remains so long as it is 255. It is 255 through, and once this is done, this will make the counter 0 in the following positive edge of the clock. That is what you see here, and thereafter it keeps on rolling around, and thereafter it increments from 0 onwards, because it is being reset here. Just to zoom here, that is the, so you can see this here. The last two are the counters. You can see 250 is the counter edge, and pre-increment is 251, and this happens to be reset count here, and advance count continues to be 1. Therefore, it is counting. Had it gone to 0, it would have reset. So, that is how you see that the counter is working. So, you can see this signal here, which resets the counter, right. This is same as this 255, same duration, because it is combination circuit as such here. That is here. So, when reset count has become 1, that is reset count is 1 if counter reg is equal to 255, then only this action take place, and this is a combinational circuit as we have seen. So, the moment 255 is encountered, immediately it will go without delay. Of course, there will be a gate delay, only after back annotation we can see. And a word of caution is, many people simulate at a very high frequency. You can simulate even at several gigahertz in this simulation, and are under the mistaken impression that they have achieved a gigahertz rate. That is simply not true, because the real life situation on the chip, even if it is ASIC latest technology also, it may not, you may not give, I mean, get more than 400 megahertz or so. So it is very misleading conception to just to simulate and jump to conclusion that it has, you have achieved gigahertz operation. For example, it depends upon the FPGA that you choose. There are wide varieties of FPGAs and different vendors, and in each vendor there are so many categories, and even in each type number, one specific type number of an FPGA, you have once again 2, 3 or 4 varieties of speeds. So depending upon the actual device, your speed will depend upon that, and a typical thing you can take is some 40 megahertz or 50 megahertz on Xilinx and even Altera chips you can have.
Because at this stage I wouldn't have decided the device, isn't it?
Yeah, we haven't.
So so 40 megahertz or 50 megahertz is probably a.
It's only an assumption based upon our prior experience. I have just put some 50 megahertz, 20 nanosecond is the time period. So that works out to be 1000 by 20. Always divide 1000 by 20, you will straight away get in megahertz, right? So that works out to be 50. So 50 megahertz is a typical value on an FPGA, and that is the reason why I stuck onto that. And if it is ASIC, I have tried 0.13 micron technology also. I have done for MPEG video compression, say DCTQ etc., which we will be showing later on in the design applications, and in that I had achieved 0.13 micron technology around 270 megahertz. You can jack it up to 300 megahertz. Only thing, synthesis will take a long time in ASIC. Okay. So we have finished the counter as such. We will now move on to the monoshot vibrator, and in this earlier I have said we could achieve for a set value of 256 clock cycles, and I said that while seeing looking at the simulation we will have an explanation for that, and we will do that. Prior to that, let me tell you that from user's point of view, it is desirable to have same delay that you have already set, because otherwise they will not be aware of this internal complications, why it should take 2 to 6, and there will be a mistaken there will be a misunderstanding, and they may get a wrong timing as such. So it is always better whenever you design a system, it is better to design looking at the user point of view. So user normally is not very knowledgeable, they can only use. So you should whatever system you design, you should go down to their level and then cater to that. So that is that must be the attitude of a good designer. So here there is a reset once again, because this is based on a counter, and that counter we call it as counter D here. D stands for delay, and the output is delay out. You get 2 clock cycles as such, and if you require you can also see the counter what present value is, otherwise use it internally. And all this process triggering will be done by here at positive edge of rising edge of the trigger, and clock is also there. Once again all transactions take place at the positive edge of the clock, and when counter register equals 255, so this will be activated, and this will be reset here, and that is how you get delay of 255 seconds. And we will see the waveform so as to get a better grasp. So now we will have a look at the waveform. So the first waveform, first I will show in unzoomed condition so that I get a clear picture, then we will zoom it. So here if you see, we have a reset here, and you may make it out fairly, and you may not be in a position to read the numbers. I will read it for you and then finally zoom it for you to view it. So to start with, we reset the system, and there is a counter, as I said, that is counter register here, and this is next, and this is as usual a pre-incrementing of the register. So you always see if this is 0 here, this is already 1. So that is how you pre-increment here in order to speed up the system. So, otherwise there is no difference between two, and you have a trigger P also, which is the trigger value, the current trigger value is here, and whatever is the current trigger value will be pushed as a previous trigger value for further processing, namely to find the rising edge of this trigger. So that we may, that is the reason why we preserve this. We preserve in the current value of trigger and then use this particular thing in the next clock cycle. So, is that clear? So, that is how you sense the rising edge, and if you see here the run delay, if you see here, for the time being I will just say it is counting by 1, 2, 3, 4, 5, 6 and so on, right, and not much information here, and we will come back here also. So, if you see here, this is the trigger here, and this is resetting the counter, and this run delay is the one which senses the rising edge of the trigger. So, trigger is going high here right at this point, and earlier value of trigger is 0, but that should have 0 must have been must be preserved in trigger P as such. You see here trigger P is actually 0 here right at this point, and whereas it becomes 1 at the rising edge of the next clock pulse, right at this. So, that makes it clear, right. Trigger P is nothing more than a previous trigger. That is how we compare the previous trigger and the current trigger, and then say decide that it is rising edge. So, the rising edge is limited to the clock period, so it can't act fast. So, like this you may have, if you are designing a complicated system such as a programmable controller or programmable logic controller, we may encounter hundreds and perhaps thousands IOs. In such a case, so many IOs might be on this rising edge direction. So, for that you can implement in this fashion. And next is we see here run delay is rising here, and here also somewhere here when the counter is 12. The reason here is I purposely made it triggered it once again when the counter is already running, just to demonstrate this is a non-retrievable. So, it does not reset here, it merely ignores. You have applied the first trigger, it started working, and while it is working, if you wantonly trigger it, right, so it will not trigger, right, it simply ignores any number of such trigger inputs. Although that rising edge of run delay is still encountered, it will be ignored because the counter is already servicing the previous trigger as such. That is what we want, and that is the meaning of non-retrievable mono. And so, the counter is clearly working 0, 1, 2, 3 and so on, and it keeps going. We will see the we will come to the end and see. And another thing is the actual output is delay output that you have seen here, that is this one, and you see that when reset had gone low, so or the reset counter D, that is also an ORing of the actual system reset as well as the reset for the counter D being equal to 255. So, if you look at the code for this, so here we have combined two resets into one statement, that is power on reset here and also counter D being equal to 255. And when any of this happen, this is an OR here, so this will go high. And now if you see here, and run delay we have already seen trigger P and trigger 1 being equal to 1. So, rising edge, that is how you sense here, it is once again all these are combinational. Therefore, when this happens, immediately it will show at the output, and these are all mere incrementing. So, what I want to show is here, yes.
This is a standard way to sense the change in clock, like rising edge or falling edge?
No, not necessarily. You can put a flip flop and realize straight away, so as a clock input, but another rule we will be violating. All the flip flops etc. you should have a system clock alone fed to that. So naturally that is not a correct way of RTL coding, right. So the best thing is to realize in this fashion. After all, clock speeds are very high. We are dealing with 40 megahertz, 50 megahertz. So how does it matter if you are delayed just by a few nanoseconds, right?
I'll modify my question.
Yeah.
To sense any change in the waveform, see for example you just sense the change in that, right? How do you go about it? Is this the way? Where previously you set it as 0 and then you check if it's 1.
Yes, my question, answer still is valid for that. What all I answered. So we are sensing the level, and but taking a decision only at the next clock pulse, because we don't have means of doing it without violating the RTL coding guidelines, right. So here we see that reset counter D equal to 1 is being checked. We are in the always loop of the at positive edge for the mono shot, and so for that we are resetting here, and otherwise increment when delay out, which is already on, the timer is on. So delay out equal to 1 is the output of the timer, and when it is on then automatically start incrementing. That is how the code has been written, and otherwise preserve the contents. And if you sense rising object run delay, that was your question, it is tested here, then only you make that delay out 1. This will happen only one time, when previous value is 0 and present value is 1 for the trigger. So subsequent thing, previous value will become automatically 1, because next clock it will be updated. So this will be encountered only at the very first rising edge, right. And if that happens, this is already 1 from that assign statement, and under that condition only this will be made 1. And once these are all, mind you, all the always positive edge clock, whatever signal that you put, they are all automatically registers. That is why once you have set the value, it will remain in for long time, indefinite time, till you veto it, right. So otherwise just preserve here, and just preserving that. So what I want to point out here is, so let us see how 256 clock cycles and 255, that is all we have to consider here in this. So now let us see what is happening here. Reset counter, we will see the waveform also. This reset counter is a combination of the power on reset as well as counter being 255. It is an extremely you have to follow very carefully, because this concerns a very sharp pulse which is going to result, and we are going to see in the diagram. We have already seen this one, there is nothing much more to add to this existing one. We will go on to the second waveform of the mono shot, where you see the end. Towards the end what is happening we will see. See, once again you have a counter D next, and here, right, and delay out is the last one, which is already high, right, and you can see the counting taking place. Once again 248 corresponds to 249 in the next value. Now let us see what happens when follow it very carefully here. So as a designer you should know the intricacies of design. So this is the most crucial step here. What is shown here is, this is the counter D reg, that is 254. What is happening after 254, it is incremented to 255 actually, right, but you see only 0 here. What is happening at that split second, you can see a very narrow pulse here. This corresponds to reset counter D, right. So follow it carefully here. So what happens when 254 is equal to 255, it goes for a very short while here. Even if I zoom it to a very large value, you will still see only a single line, because we are dealing with the simulator and there is no gate delay coming, but fortunately the simulator is very well done and they do not have a bug on that score and can at least show a very fine line there, right. But in real practice what you look at the code. See here the code is when counter is equal to 285, that is precisely it has happened, and the moment that happens this goes to 0 because this is a combination circuit. So this is nothing but an OR gate. So you get when the moment counter touches 255 and immediately after a delay of this OR gate, right, this will get reflected here. So are you getting it? If this happens, what happens to this statement? That is reset counter D, right. So what has happened here is, follow this carefully, this is the crucial thing. We have a positive edge of clock just now arrived which made the counter to 255 and immediately following this within less than a nanosecond or around a nanosecond, what is happening is this assign statement of reset control D is making it 1. So what happens if that is 1, earlier it was 0. So what is put here as a condition is or positive edge of reset control D. So immediately this condition is satisfied and right at the positive edge following that this is also satisfied, so it immediately enters within a nanosecond. So it satisfies this condition and then goes on to clearing the counter itself, right. That is precisely what you have, and simultaneously delay out is also made 0. That is how you get that. So looking at the waveform once again, you see here 254, this is the counter edge, the last one, right here, and this is the delay out. Finally it is still 1 here, and now when it is 254, at this point of time it instead of 0 it has actually 255 has come over there, and because of the combinational action here, that reset control D, that is here, right. So you can see this, it has it's activated here for a split second only, it is there, and what happens the moment 255 this is reset counter is 1, 255 is cleared to 0, that is what we have seen, and also you should have the output also 0, right, at precisely at that point of time this is happening, right. And so as a designer you should be aware of all these things. One slight mistake in the code will make it topsy-turvy, right, and yes.
Am I not supposed to have a glitch after 254 also?
Here for in this you want this is synchronous circuit, so there should not be any glitch. Glitch will appear only in combination circuit. This appears to be a glitch, but it is not a glitch. It is only acting as per the command that we have given. The instruction that you have given is responsible for this.
But you said momentarily it's 255, right?
Yes.
Momentarily. Is it not supposed to be reflected there?
Here. So it is so fast it is happening, right. So because the moment it goes to 255 and you may be perhaps let us examine after back annotation, let us see whether that shows up. You are right, that is a point we can examine later on, right. Right now we can't because the simulator does not contribute to the gate delays. That is why I said instead of 50 megahertz which is shown here, suppose I make it 2 gigahertz or even more, this will still show up, and unfortunately many people have jumped to conclusion based on mere simulation. So the real story will show up only when you have taken it through the entire design flow, which we have already seen in a flow chart earlier. And next is one more point I would like to mention is earlier we had this is 254. In the earlier case we saw that it is this delay out, make a note here, this delay out is going high here and remains high till it was 254, but this is corresponding to this 0 here, 0 itself is spread over a 1 clock pulse. So in other words, last one was 254 plus 0 if you add, you have got 255 clock cycles delay, that is what you have got. This proves that whatever is the setting you get precisely that, right. And now another point is Suppose earlier I said 256 cycles. Why that happened is the code was different. I did not take that reset counter D as a asynchronous, that is an asynchronous way of setting in this. So earlier what I had done is that reset counter I had taken inside itself. So when reg is 255, I make a decision only there. Actually it was here. See, here we are saying reset, although we say here, and this is for combining the power on reset as well as the counter reaching 255. Now earlier what I had done is I did not combine this. Why I combined here is I have also said always block is priority encoder, therefore we have to limit number of ifs, else if to less than 4 or 5. By combining the two I have reduced by 1. So that is the advantage, thereby speeding up the operation, and of course with a little understanding complexity which we have already cleared. And you can see here how many ifs, you can just see here, one if is there, then 1 2 else if 3, right, just with 3 we have made, otherwise it would have reached 4 with the earlier thing. So why 4 is here that if reset will be negative edge reset, first if we had put it as here, instead of this we had used a negative edge reset underscore n, and because we have combined that, here it happens to be the same condition, whether this condition takes place or this. In earlier way of representation, this has been separated out, this reset power on reset has been dealt here, and the actual counter reaching 255 had been dealt somewhere here in between. So it added one more else if, thereby slowing the system, and also instead of 255 set point we got 256. The reason being that when it touches 255, in this case you would have very easily seen that 255 clearly for one complete cycle. In this what we had seen here is 254. In the previous case, had you implemented that one, instead of after 254 it won't become 0, it would go to 255 and next only it will go to 0, in which case that is because counter reg is activated in the present clock cycle, which will be taken into consideration only the arrival of the next clock. So in other words, in the previous design it has to wait for the next here. Are you clear about this? Thereby 255 plus the 0, that 0 remains same. So now you would have got, earlier you would have got 256 clock cycles, and that is why I said by looking at the waveform you can understand better, that is why I deferred on those days, and also I changed it to suit this. So are you clear about this? Then we will move on to shift register. Yes.
But still that glitch is likely to be there, isn't it?
Which one? No, that won't be there, because that signal itself will be removed. This signal is the result of ORing two things, right? Reset counter, reset being active and counter being 255. We have clubbed, that is why this, it is not a glitch as I mentioned, right. So we have in RTL coding guidelines I think we saw how glitches are found, it is because of difference in path delays. So now we will move on to the shift register. So in this shift register we have here, so we had a 16-bit shift register and a data out can be had here, and we had two types of shift register, data out 1, data out 2, both primarily same, except that the way of writing in assign statement for shift was different. One was with 2 less than symbol, the other one was to concatenate simply, right. There is a clock input and a shift here, and vacated bits are filled by 0, and there is also a power on reset here. We start with the contents 1010 and then right shift by 1 bit, because this is a right shift by 1 bit. So you should get this. So let us look at the waveform. So here what we do is, this is the data out 1, I think I will zoom it further. So, earlier I think you had asked this question. So, can we have 16 bits represented, right, and that is precisely what we have here. So, what is happening here, whenever there is a reset that is active here and the clock is free running, it can start any time or after the reset, and it does not really matter, because reset is asynchronous active low. Asynchronous means whenever that happens immediately it will take an effect. So, whereas in synchronous it will take effect only when the clock arrives. So, this is asynchronous for the reasons we have already covered earlier, and we see that this data on is preset by this value whenever reset is encountered. That is why you have the same 1010 appearing here, and so also data out to, which is alternative approach for the shift, and once again a corresponding next will be there pre shifting and here, right. So, data out is not, it is here. So, it is enough if you have a look at the data out. Actually we will just have one data on next. If you see, it will always pre shift. So, because right shift by 1 bit, so 10 has become 010101 here, because it was right shifted. So, this will be assigned to this only with the following clock edge. So, if you will have a look, you can see that this is the data on data out 2 are exactly same, because it is same problem solved in two different ways, and if you look at it, this pattern will keep on shifting. So, it is there in the next one, in next two slides we can see. So, if I will once again zoom this here. So, coming to these are all the data 1, data 2. So, the first value was 1010, with the arrival of the next clock pulse it has become 0101, and both are same. You can just have a look all by yourselves, and then you keep on looking at it, see 2 zeros 1, so all the other bits are there, that means it is clearly right shifting here, and this is pre increment, this will take effect here. So, only at the next stage, and so on it goes, and the last waveform gives the fag end of that thing. So, once again we will zoom here. So, if you look here, the same pattern will be continuing. You can see 101 here, all are zeros, and here all are zeros, this 1 will get dropped. So, what you have is 10 here, and then this 1 will move here as shown here, and finally that one also will disappear, right. So, that is how you see a shift register working, right. So, next we will move on to so we had seen a parallel to serial converter. There is a reset, you can set the data and then load it and then shift once you have loaded. So, what it does is we have a 16 bit parallel information which will load into the counter shift register here, and then shift either left or right depending upon this control RLN, one being right shift here and at the positive edge of the clock, so long as shift is valid, and there will be a data out here which will be the single bit because it is a parallel to serial, and so whether MSB of the data arrives or LSB arrives, it depends upon whether it is right shift or left shift. For left shift 15 will go out here. So, this we have already seen the code, and we will look at the waveform because we have already seen the code, and there will be an end of conversion once all the bits are serviced, and we also had internally one register allocated for keeping track of number of bits processed, right. So, here as usual a reset is applied, and this is set data. Here also we are setting the same 1010 pattern, and a shift register, what happens internally, there is a shift register 16 bit, and that is preset to the same 1010 because that is what we want, and at the positive edge of the clock because code has been written like that, and this is the counter to keep track of the number of bits. Now, you need to send 16 bits, so it is initialized to 16 here, and every bit going out, this will be decremented, as you can see, going to 15 here, 14 here. Why a long gap is, we have first loaded this value by activating this high, and it goes low only here, and then simultaneously we will make the shift control high, so that with the next arrival of the next positive edge of the clock, it starts and the counter starts decrementing, as well as it has output the value. Data out is here. To start with, it is all 0 here, and here what happens, okay, I will just zoom this so that you may know. So, this is the shift register and this is the counter, this is the data out, and a data valid and end of conversion is also here. All these are 0 here, data out, data valid and end of conversion, right at the point of loading the value. So, now what is happening, so remember the last this one is the data out and it is in 0 here, and here what happens, so here it is, I think, what is this here, this is R stands for this is a left shift here. It is initially left shift, but it is now right shifted here. So, it is made 1 here. So, hereafter this will be right shifted, right, including for the very first bit, that is why it is going right here, not here, right. So, now 1 0 1 0 we started with, now you can see that it is shifting 0 1 0 1 here, and also it is a right shift. So, actually it was 0 here, first bit. So, what you need to get is, this is the output, this one. So, data out is this one, this immediately next. So, it is 0 here, because first bit was 0, and the second bit happens to be 1, because this is 1 here, and this is also right shifted. So, like that you can see it is right shifted, as well as the last bit goes over to this. You can just see, you can see in the next, because this is the fag end of this, and you can see here, and it goes on there. Only unfortunately I did not show the in between, and only towards the end I have shown. I think you should, you can make it out yourselves, no problem. So, here you see that count, I will once again blot it out. This is right shift remaining high here, and you can see that 3 2 1, this is the count up, the last value, and every time it is going to here what has happened, this is a left shift, I think, yes, right. So, what, so I have forgotten to take on the in between, right. So, I have done both right shift as well as left shift to show, but I should have shown 2 more waveforms. Since you have the code, you can do it yourselves. So, this only to show how the how to analyze the waveform as such. So, you see that it is working, right, for this one is here and one goes to this being left shift here, and finally 0 is the thing, and the corresponding outputs you can see at every point of time. Have a look at this, it has to keep on toggling from one to another, because alternate values are 1s and 0s. So, this then what we will do is we will go on to the state machine, and yes.
This is a general question. You talked about always at positive edge, negative edge.
Yes.
How do you go about doing level triggering?
The level is same. I mean, you sense the level, immediately take action. It can be within the sequential circuit or outside it. If it is outside, you can use assign statement, a mux statement you can have. If a particular level is 1, immediately let the output change using an assign statement. If it is within a sequential circuit, there also you can use any signal, even an asynchronous signal you can use inside. If such and such thing takes place, then take action, and that is precisely what we have already written in almost all the codes that we already covered. Are you clear?
I can't say something like you said pos edge, negative edges. Can't I say level edge or something like that? Always set level edge or something. No.
Yes. You have only to if let us say whatever signal that you are considering, let us say signal x, that is level you have to sense. If within an always block, a positive edge clock, etc., you write if x equal to 1, then you do this. So that is what you want. So that edge can, I mean, it is not an edge but actual level, right. If you want level to be 0, you can do take action based on that. You have only to say if x equal to 0. So right. So we will consider state machine here. So this is going to be involved a bit, some running to 4 or 5 slides as such, and so we have seen in the PowerPoint this. So this is state machine, and S0 through S3 we have already covered this also, as well as the code for this and test bench for that. So it is enough if you just have a look and the waveform, you can make it out. For example, if it is S0 and so long as its input is 1, you remain there, and also lighter an LED, any output can turn on the output Z0 here, and for every other states you have Z1 representing the same state. So based upon the input conditions in 1 and in 2, it is going to from one state to another, it will be going to. So we can see one of the waveforms here. To start with, it is in reset here, and in 1 and in 2 are here. So both are zeros here. Now let us see what is happening here. All are zeros here. So what will happen here is that, and all the outputs are cleared here because of the reset here. So it only shows the reset condition, nothing much in this. So if you go to this second one, you can see it is advancing. This is state field, last one. It is in 0 0 condition, and very first state which is going to state, and change. So from 0 0 condition it goes to 1 0, depends upon what inputs are. Here input 1 is 1 and input 2 is 0, right. So this means input 1 is 0, it has to be in the same state, that is what we have already seen, and if it is 1, it has to go to second state. It is going to second state 1 0, and it will go again to next state 0 1 depending upon the input condition. Say if it is here, it is input is 1 here and 0 here, and but now it is in 1 0 state, that is S1 state. In S1 state, what will happen? In 1 is 1 and in 2 is 0. S1 state is here, right. If in 1 is 0 and in 2 is 1, it remains in the same state, right. And so we can see, we will see at random because it is two involved. So we will see before we wind up for today. So we will see at random a few of them. So let us say 0 1 S1 state here, we will see one more state here, say it is S3 state. In S3 state what happens, let us have a look. So and corresponding depending upon the state, that particular light also will go up. See for example Z1 is high here, so that is because we are in S1 state, that is what we want there, right. And here in 1 1 state what happens, say the clock is arriving here. So, only at the positive edge of the clock the transition will be made, that is why it is extending here, right. So, this will get reflected only later on, right. And in 1 state, let us see what is the input here. In this case 1 and 1, both are 1 and we are in 1 state. Let us see what happens there. We are in 1 state and both are 1. So, it has to remain in the same 1 state and right, is it remaining? What is happening here? It is this is 1 state. So, it goes to Z3 only at the rising at the pulse here, right. So, now what is happening here? What is the input here after this? We have again input is changing here, right, 0 0 here. You see here it was 1 1 here, but now it is 0 0. So, what should happen is in S1 state we should have here, if it is into is 0, should go to S0. So, we will continue with this in our next class as such. Thank you.